Okay, so for FRQ number 4, we have a uniform rod that has a mass of m1 and a length of L, and it's initially at rest on a frictionless horizontal surface. The moment of inertia of the rod about a center of mass is given to be m1 times L squared divided by 12. We also have a point mass m2, and it has an initial velocity of v, and the initial velocity is perpendicular to the rod. The point mass m2 will collide with the rod m1 after moving for a while, and after the collision, the mass m2 will have a velocity of negative v over 2, meaning it will have half of the velocity initial, and it will be pointed in the opposite direction. Here are the two diagrams of what is happening, and this is basically before and after. And part A wants us to use principle of conservation of linear momentum to determine the velocity of the center of mass of the rod after the collision, v prime. Okay, so part A. If linear momentum is conserved, that means the total linear momentum initial is equal to the total linear momentum final. All right. For total linear momentum initial, we only have linear momentum of m2 initial, because that's the only object moving initially. For linear momentum, the total linear momentum final, we have the linear momentum of m1 final plus the linear momentum of m2 final. Okay, so for the linear momentum of m2 initial, that's equal to m2 times the initial velocity, which is just v. The linear momentum of m1 final is equal to m1 times its final velocity, which is v prime. The linear momentum of m2 final is m2 times its final velocity, which is negative v over 2. And now I want to solve for v prime, right? So what I'm going to do is I'm going to combine these two terms by adding this to this side. So adding this to this side, I'm going to get 3 over 2 m2 times v. And that's going to equal to m1 v prime. I want to solve for v prime, so I'm going to divide m1 to this side. So v prime is going to be equal to 3 times m2 times v over 2 times m1. And that is my velocity of the center of mass of the rod after the collision. Okay. Part B wants us to use conservation of angular momentum to determine the angular velocity of the rod about a center of mass after the collision. Alright, so similar concept. If angular momentum is conserved, the total angular momentum initial is equal to the total angular momentum final. For total angular momentum initial, we only have the angular momentum of m2 initial, because that's the only object moving. For total angular momentum final, we have the angular momentum of m2 final plus the total angular momentum of m1 final. For angular momentum of m2 initial, that is equal to m2 times v times the moment of arm, r. Angular momentum of m2 final is m2 times the final velocity of m2, which is negative v over 2, times the moment of arm, which is r again. The angular momentum of m1 final can be represented with the moment of inertia of the rod times its angular velocity, omega. And omega is what we're trying to solve. Alright, so I don't know r, so I have to define it first. So here is a diagram of the problem again. So here's a rod, M1, and here's a point mass. It's gonna hit some point right here, somewhere right here. So M2 right here. This is the center mass of the rod, and we are given that the total length of the rod is L. Knowing that the total length of the rod is L, we know this is going to be L over 2. We are also given that this length right here is L over 6. And if we want to find the moment of arm of M2, this is basically this distance right here, which we can find by subtracting this from this. So R is going to be equal to L over 2 minus L over 6. L over 2 minus L over 6 is L over 3. So that is our R. So I'm going to plug that in right now, as well as my moment of inertia for the rod. So M2 times V times R, which is L over 3, is equal to M2 times negative V over 2 times R, L over 3, plus the moment of inertia for the rod is M1 times L squared over 12, and we still have omega, the angular velocity, which is what we're trying to solve. So these two terms are alike, so I'm going to add this to this side. M2 V times L over 3. This can be added because there's a negative here, so plus M2 times V over 2 times L over 3, and that's going to be equal to M1 times L squared times over 12 times omega. So I can factor out some stuff from here. I can factor out an M2, I can factor out an L over 3, and that's it. So this side is going to be equal to L over 3 M2 times if I factor out this right here, I'm going to be left with D for this term. For this term, I'm going to be left with 1 half V, and for this side stays the same. M1 L squared over 12 times omega. So I want to solve for omega, so what I have to do is multiply 12 over and divide by M1 and L squared. Alright. Wait, actually, first of all, I need to reduce this down. Over 3 M2 V plus 1 half V is 3 over 2 V. Alright. Now I'm going to do what I said. So I'm going to multiply 12 over and divide by M1 L squared, leaving with omega. So what's going to result is, first of all, these two cancel. If I multiply 12 over and divide by 2, I have 6 in my numerator. I still have M2 in my numerator and V in my numerator. Dividing by L squared, 1 of the L is going to cancel, and I will still have 1 L at the bottom, and M1 is going to be at the bottom, so M1L. So that is my angular velocity of the rod about center mass after the collision. Alright. Now part C wants us to determine the change in kinetic energy of the system resulting from the collision. So if we want to find the change in kinetic energy, we must first find the initial kinetic energy and the final kinetic energy, and then we subtract them. So the total kinetic energy initial is what we're trying to find first. So KEI total initial is equal to just the KE linear of M2 initial, because that's the only object moving at a time, and this is going to be equal to 1 half times m2 times v squared. So that is my KEI total. Now for my KEF total. Now for KEF total, I have 3 different kinetic energies. I have KE linear for M2 final. I also have KE linear for M1 final. And I also have KE rotational for M1 final. Alright. KE linear M2 final is equal to 1/2 times M2 times the final velocity squared, which is -v/2 squared. KE linear of M1 final is 1/2 times M1 times the final velocity of M1 is v prime, so v prime squared. KE rotational of M1 final is equal to 1/2 times the moment of inertia of the rod times omega squared. Okay. Now I'm going to plug in what I've solved in part A for v prime right here, and solve it. Plug in this for omega. So 1/2 M2 -v/2 squared. This term stays the same. And for this term, I'm going to plug in v prime. So 1/2 times M1 times v prime, which is 3 times M2 times v over 2 times M1, and square that. I have 1/2. I'm going to sub in I rod as well, and that is equal to 1/12 times M1 times L squared. And I'm going to sub in omega, this over here. So 6 times M2 times V over M1 times L, and then square all of that. Alright, now I'm going to reduce all, or just multiply these two, distribute all of the squares at this point. So the first term, 1/2 times M2, distributing the square, I'm going to have V squared over 4. For this term, I'm going to distribute the square as well, so 9 M2 squared times V squared over 2 squared is 4 M1 squared. For this, I'm going to distribute this square, so 1/12 times. All this stays the same first, and so okay, 6 squared is 36. M2 squared V squared over M1 squared L squared. All right. So from right now, I can cancel a lot of stuff from this term. So I have M1 cancel one M1 down here. L squared can completely cancel with an L squared here. And for this term, I can also cancel M1 with an M1 right here, leaving only M1 at the bottom. And now I can reduce those terms. All right. So this term is going to be equal to M2 times V squared, and 2 times 4 at the bottom is going to be 8. This term is going to be equal to, so I have 9 on top, so 9 times M squared times V squared. For the bottom, I have 2 times 4, which is 8. I have an M1, only one M1 left, so M1. And for this term, this messy term over here, 36 divided by 12 is going to be 3, so I have 3 on top, 3m2, wait, it's m2 squared. Yeah, m2 squared here. Oops. 3m2 squared times v squared over 2, and I only have an m1 at the bottom since this one canceled here. 3m1 here. All right. So these two terms are alike. So what I'm going to do is I'm going to times 4 to this term, 4 over 4, which will give 12 over 4, and 12 over 8, if I do that. So this is going to be equal to 12 over 8 m2 squared v squared over m1 here. So once I do this I have a common denominator with this now, so I can add those two. So my final answer for KE final is m2v squared over 8, which is this term, stays the same, plus this is 21 m2v squared over 8 times m1. All right, now I have to subtract. I wanted to find a change in kinetic energy, so I have to subtract this and that. So change in KE is equal to total kinetic energy initial, after or final, minus total kinetic energy initial. My total kinetic energy final is m2v squared over 8 plus 21 m2v squared over 8 m1, and my total kinetic energy initial is 1, so subtract 1/2 m squared v squared. All right, now these two terms are alike, so first I'm going to times once again by 4 over 4 to this term, and that gives me 4 over 8 m2v squared. Now that I have a common denominator, I can combine these two terms. Wait, this is negative, by the way, since there is a negative right there. So combining those two terms, my final answer is going to be, this one stays the same, so 21 m2 squared v squared over 8 m1 minus, so this and this makes 3 over 8 m2v squared. And that's my answer. Sorry for the word fumbling, but anyways, there.